Welcome to Late Night History. Tonight, there is nowhere you need to be and nothing you need to do except to let your breathing slow and your thoughts grow quiet while we follow something very small on a very long journey. We are going to follow a single drop of rain, just one, and we are going to follow it down through soil and stone, down into the dark, and we are going to watch it do something that should be impossible. We are going to watch it carve a cathedral out of solid rock. Not with force, not with a hammer or a chisel or any kind of violence, only with patience and with a chemistry so gentle you would never feel it on your skin. So settle in. Let your shoulders drop. There is no hurry here because the story we are telling unfolds over spans of time so vast that 1,000 years is barely a single breath. Picture the rain falling. Somewhere over a green hillside in a country that does not matter for now, the sky lets go of its water and the drops begin their slow descent. A single drop falling through the open air is almost perfectly innocent. It is nearly pure water, faintly acidic, but only just because as it falls, it brushes against the carbon dioxide in the atmosphere and takes a little of it in. That alone would never carve anything. That drop, if it landed on a slab of limestone and simply sat there, would do almost nothing at all in a human lifetime. The rock would outlast it 1,000,000 times over. So if the story ended in the open air, there would be no caves, no chambers, no stone curtains hanging in the dark. The drop would be far too weak. But the drop does not land on bare rock. It lands on soil. And this is where the quiet miracle begins. Beneath the grass, beneath the moss and the fallen leaves, there is a hidden world that is breathing. The soil is alive. It is thick with roots drinking and exhaling, with insects and worms turning the earth, and above all with the slow, endless work of decay, as last autumn's leaves and last century's wood are taken apart by countless unseen things and returned, molecule by molecule, to the ground. All of that living and dying releases carbon dioxide. And because the soil is closed and packed and full, that carbon dioxide does not simply drift away into the sky. It builds up. It collects in the tiny pockets of air between the grains of earth. The air down there in the soil can hold 10 times, 50 times, even 100 times more carbon dioxide than the open air above it. The soil is a sealed lung, exhaling into itself, never quite letting go. And our raindrop sinks into all of that. As the water soaks down through the living soil, it passes through that rich, heavy carbon dioxide-laden air, and it drinks it in. It takes the carbon dioxide into itself far more greedily than it ever could up in the open sky. The water and the carbon dioxide meet and join, and they become something new. They become a faint acid. Carbon dioxide, which we can write as CO2, combines with water, H2O, and the two of them together make carbonic acid, which the chemists write as H2CO3. That is the whole of the first secret. Rain made sour by the breath of dead leaves, water turned into a weak acid by passing through the buried exhalation of a living soil. A tool sharpened in the dark before it ever reaches the stone. Now the word to hold on to there is weak. Carbonic acid is a weak acid. It is nothing like the acids we are taught to fear, the ones that hiss and smoke and burn through metal in seconds. You could hold this acid in your hand and feel nothing. In fact, you have tasted it many times because it is exactly the gentle sharpness in a glass of sparkling water, the same faint tang that comes from carbon dioxide dissolved in liquid. That is the acid that carves the cathedrals. Something so mild you would drink it for pleasure on a warm afternoon. And that gentleness, that weakness, is the entire reason this story is so slow. And so it is the entire reason it is so beautiful. because now the acidified water, sinking further down, finally reaches the rock. And the rock it reaches is limestone. Here the faint acid begins its patient work. The carbonic acid in the water meets the calcium carbonate of the limestone, calcium carbonate being the mineral that makes up the stone, written as CaCO3, the same substance as chalk, the same substance as a seashell. And when the weak acid touches it, a reaction begins. The carbonic acid and the calcium carbonate combine, and the solid stone, grain by tiny grain, is taken apart. It dissolves. The hard rock turns into something the water can carry away. The calcium drifts off as a dissolved ion, and what was once solid stone is now simply held in the water, invisible, carried along in the flow like sugar stirred into tea. The rock has not been broken. It has been quietly persuaded to come apart and float away. That is the heart of everything. Acidified rain meets limestone, and the limestone slowly dissolves and is carried off into the dark. The acid does the dissolving, and the water does the carrying. And because the acid is weak, the dissolving is achingly, almost unimaginably slow. A single passage of water leaves behind only the faintest trace of its work, a film of stone too thin to see, removed from the walls of a crack you could not even fit a hair into. There is nothing dramatic about it. There is no sound, no spark, no sudden collapse. There is only the steady, patient, drop-by-drop persuasion of stone, going on in total darkness, going on whether anyone watches or not, going on across spans of time so long that whole mountain ranges rise and wear away while the work continues. And that is the thought I would like you to carry down into sleep tonight, that the grandest rooms ever hollowed out of the earth were not blasted or dug or built. They were dissolved gently by sour rainwater over so many years that the number means almost nothing to us. The cathedral is not carved at the speed of a chisel. It is carved at the speed of a fingernail growing. Slower, even. And yet, given enough time, that whisper of acidity will eat its way through a mountain. But before we follow the water down into the dark, I want you to know something about the stone it is dissolving, because the rock itself has a secret, and it may be the strangest part of this whole story. The limestone is not really rock at all, not in the way we usually mean. The limestone is made of the dead. Reach out in your imagination and lay your hand flat against the cool, grey face of a limestone cliff. It feels like the most permanent thing in the world. Solid, ancient, unmoving, the very definition of stone. And yet, if you could look closely enough, closer than any eye can see, you would find that this stone is built almost entirely out of the bodies of creatures that once swam and drifted in a warm and shallow sea. Limestone is, overwhelmingly, the compacted remains of living things. It is made of coral, of seashells, of the calcite plates of algae, and of the tiny, intricate shells of creatures called foraminifera, single-celled beings smaller than a grain of sand that built themselves delicate cases of calcium carbonate, lived their brief lives drifting in the sunlit water, and then died and sank to the seabed in numbers beyond counting. For millions upon millions of years they rained down through the water like a slow and endless snow, the shells of the dead settling on the floor of the ocean, layer upon layer upon layer, piling deeper and deeper until the weight of all that accumulation pressed the lower layers together and cemented them into stone. A graveyard pressed into rock. An ocean's worth of small lives compacted into something hard and grey and seemingly eternal. And then, in the slow turning of the earth, that ancient seabed was lifted up. The forces that crumple continents and raise mountains took the floor of that vanished sea and pushed it upward out of the water into the daylight until the place where corals once grew became a green hillside under a rainy sky. So when our raindrop, turned to weak acid by the breath of dead leaves, sinks down and begins to dissolve the limestone, here is what is truly happening. The water of today is dissolving the ocean of 100 million years ago. The faint acid is eating away at a drowned sea that has been lifted into the air. The shells of creatures that died before the dinosaurs walked the earth are being unmade one by one and carried off into the dark to be set down again somewhere else. Let that settle over you for a moment. The solid rock is a resurrected ocean. The cathedral that the water will carve is built out of a graveyard of the sea, hollowed by rain into rooms vast enough to lose a city in. Everything that follows in this long, slow night is the meeting of two ancient things: the water made gently sour by life on the surface, and the stone made entirely of death in the deep past. Where they meet in total darkness, the most extraordinary architecture on Earth begins to take shape, grain by grain, drop by drop, century by century. And before we go on, since we have a long and quiet journey ahead of us tonight, I would love to know where in the world you are listening from. There is something I find genuinely comforting in the thought of all of us, scattered across the surface of this old planet, lying in the dark in different countries and different time zones, all settling into the same slow story. So if you feel like it, leave a word in the comments and tell me where you are. And if you are new here and you would like more of these slow, unhurried journeys into the deep past and the deep places of the earth, you might quietly subscribe so the next one finds its way to you on some other restless night. There is no rush. The button will still be there in the morning, because that is what tonight is for. Not to learn exactly, not to remember every term or hold on to every fact, just to be carried slowly down into one of the earth's great mysteries, and to let the going down itself be the thing that loosens you towards sleep. You are allowed to drift. You are allowed to lose the thread and find it again, or not find it at all. The water has been doing this work for millions of years without anyone watching, and it will keep doing it long after we are both asleep. You can let go and trust it to continue without you. So let us go back up to the surface just for a little while before we follow the water down, and let us learn the shape of the land where all of this happens, because there is a name for a landscape that is being slowly eaten by acidified rain, and that name has its own quiet story. The name is karst. It is a strange little word, karst, and it comes from a real place. There is a plateau, a high stretch of rocky ground that sits along the border of what is now Slovenia and northeastern Italy, near the Adriatic Sea. In Slovenian it is called the Kras, and in Italian the Carso. It is a hard, pale, stony country full of bare grey rock and hidden hollows where streams have a habit of vanishing into the ground and rivers run unseen beneath the fields. It was here, in this rugged borderland, that scientists first looked closely at this kind of dissolving landscape and tried to describe it properly, to understand why the land behaved so strangely, why the water disappeared, why the rock was full of holes and grooves and sudden pits. And because this plateau, the Kras, was the place where it was first carefully studied, the whole world's worth of dissolving limestone landscapes came to be named after it. We took the name of one stony plateau in Slovenia and gave it to every place on earth where rain quietly eats the rock. Karst. A small word from a small region, carrying within it a planet's worth of slow geology. And here is the thing that surprises most people when they first hear it. This is not some rare and exotic kind of land, tucked away in a few odd corners of the world. Karst is everywhere. Roughly 1/5 of all the ice-free land on the surface of this planet is karst, or something very much like it. 1 acre in every 5, give or take, stands on limestone or similar soluble rock that the rain is slowly working on. Whole regions, whole countries rest on a foundation that is being patiently dissolved from within. And it is not only the empty wilderness. A comparable share of all the people alive on Earth, something close to 1/5 of humanity, draws the water they drink from karst. Their wells and their springs tap into the hidden plumbing of dissolved limestone, into the underground rivers and the flooded passages that the acid has opened up over the ages. So this is not a distant curiosity. For a great many people, the water in the glass beside the bed comes in the end from exactly the kind of slow stone dissolving we are following tonight. The cathedral and the kitchen tap are part of the same hidden system. Now, before the water ever disappears underground, it leaves its signature on the surface of the stone, and once you know how to see it, you can read the whole patient story written right there on the bare rock. Go to a place where the limestone breaks through the soil and stands open to the sky, where the rain falls directly onto naked stone and runs across it before it can sink in. Look closely at the surface, and you will see that it is not smooth, it is fluted. It is carved into countless little grooves and ridges and channels, like the rock has been raked by some impossibly fine comb, like the grain of weathered driftwood, only in stone. Sharp little crests stand up between hollow runnels, and the runnels twist and join and run downhill, following the path the rainwater takes as it sheets across the surface. These grooves have a name, 2 names really. They are called cairn, or sometimes lapiers, and every one of them is a tiny record of the same chemistry we have been following. Wherever the acidified rainwater ran a little longer, lingered a little more, it dissolved a little deeper, cutting the runnels. Wherever the water ran off quickly, the rock stood proud, leaving the sharp ridges between. The whole fluted surface is simply the map of where the water went, etched into the stone over centuries by nothing more than the gentle sourness of rain. To run your hand across cairn is to feel the fingerprints of 10,000 storms, each one taking away a film of stone too thin to see, all of them together carving the rock into something that looks almost combed. It is the first visible proof, right there in the daylight, that water really can shape solid rock, given enough patience. But the cairn are only the beginning, only the surface. The water that carves them does not stay on the surface for long. Sooner or later, on a karst landscape, the water finds a way down. And often it finds that way down quite suddenly and quite completely, in a way that has unsettled and fascinated people for as long as they have lived on this kind of land. Imagine a stream, an ordinary little stream running cheerfully across a meadow, the kind of thing you might follow on an afternoon walk, expecting it to lead you on and on toward a river, and eventually the sea. You follow it down the valley, and the water chuckles over its bed of stones, and everything is as it should be. And then the stream reaches a particular spot, and it simply disappears. It runs up to a hole in the ground, an opening in the rock, and it pours straight in and vanishes, swallowed whole by the earth. One moment there is a living stream, and the next there is only a dry, empty bed of stones running onward to nowhere, and a quiet hole where the water went down into the dark. This place, where a surface stream is swallowed underground, has a name as well. It is called a swallow hole, which is a wonderfully plain and honest description of exactly what it does. It is also called a ponor, which is the older word, borrowed like karst from the languages of that same Slovenian and Balkan limestone country where so much of this was first understood. A ponor, a throat in the ground, drinking a river. And this is the doorway. This is where our long journey leaves the surface behind. The acidified water that turned bare stone into fluted cairn that gathered itself into a stream and ran across the meadow, now pours down through the ponna and out of the daylight altogether, down into the limestone, into the cracks and the passages it has spent ages opening, down into the patient, lightless world where the real carving is done. Everything we have seen so far, the sour rain, the dissolving stone, the drowned ocean lifted into the air, the fluted surface and the vanishing stream, all of it has only been the way in. Stand for a moment at the edge of that swallow hole in your mind and listen. The stream pours down into the dark, and the sound of it fades quickly, swallowed by the depth, until there is only a faint and distant murmur somewhere far below, and then not even that. The water is going down into a place where the sun has never once reached, where it is dark in a way that the surface never truly is, a darkness that has held for longer than there have been creatures with eyes to be blinded by it. And in that darkness the weak acid is still at work, still dissolving the resurrected ocean grain by grain, still carrying the stone away to set it down again, somewhere deeper still. We are going to follow it down there. We are going to follow the water past the swallow hole and into the hidden rooms it has opened, and we are going to see how the same gentle chemistry that combed the surface into grooves can hollow out chambers so vast they could hold whole fleets of aircraft, and can hang the ceilings of those chambers with stone made to look like cloth and candle wax and frozen waterfalls. But there is no need to hurry toward any of that. The water took an unhurried path, and so will we. For now, simply hold the picture of the single drop. The rain falling on the green hillside. The drop sinking into the living soil and drinking the breath of the dead leaves, growing faintly, gently sour. The weak acid, mild as sparkling water, meeting the grey limestone that is really the pressed-together graveyard of an ancient sea, and the stone beginning ever so slowly to come apart and float away into the dark, 1/10 of a millimetre at a time, century after century after century, in a place no one will see for 100,000 years. The rain is still falling somewhere on some limestone hillside, even now. It has never stopped. Long before anyone gave the landscape a name, long before there was anyone at all, the sour water was already finding its way down through the punnas and into the dark, dissolving the old sea, hollowing the rooms, hanging the ceilings. It was working while the first cities rose and while they fell. It is working tonight while you lie here in the quiet, drifting towards sleep. And it will go on working, drop by patient drop, long after this night is over and forgotten. So let the stream pour down into the swallow hole and let yourself follow it, slowly, without effort, into the dark below the world. We are going down now, past the fluted surface and the vanishing water, into the place where the cathedrals are carved out of solid rock by nothing more than patience and faintly sour rain. And down there, in the lightless rooms that the water has opened, the second half of the secret is waiting, the part that explains not how the stone is taken away, but how, in the very same breath, it is given back. Begin with where it all starts, because the chemistry is gentler than you might think. A single drop of rain falls out of the sky, and on its way down it brushes against the carbon dioxide already in the air, and it takes a little of that gas into itself. That alone makes it the faintest bit acidic, barely worth mentioning. But the rain is not finished. When it lands and sinks into the soil, it enters a hidden world, thick with breath. The roots of plants are breathing down there in the dark. The dead leaves and the fallen wood are slowly rotting, and rotting is its own kind of breathing, a slow exhale of carbon dioxide into the spaces between the grains of earth. The air trapped in the soil can hold 10 times, even 100 times, more of that gas than the open sky above it, and the water drinks it all in. This is the quiet secret of how soft water learns to eat stone. The carbon dioxide dissolves into the water, and the two of them join to make a thing called carbonic acid. You could write it as a small equation if you wanted to, carbon dioxide and water becoming H2CO3, but you do not need to remember any letters tonight. You only need to remember that the rain has now become a weak acid, not a fierce one, not anything that would sting your skin or hiss against metal. It is mild, about as mild as the fizz in a glass of sparkling water. And yet that gentle sourness is the only tool the whole vast machinery of the underworld will ever use. The water carries its faint acid down to the limestone, and there the second part of the chemistry happens. The acid meets the calcium carbonate that the rock is made of, and slowly, molecule by molecule, it pulls the stone apart. The solid limestone becomes calcium and bicarbonate dissolved in the water, invisible now, carried away in solution like sugar stirred into tea. The reaction would look like this if you cared to see it written: H2CO3 meeting KCO3 and becoming calcium and bicarbonate ions drifting free. But the shape of it matters less than its pace. Because the acid is weak, the dissolving is slow. That is the whole of it. A strong acid would tear the rock open in an afternoon and leave nothing graceful behind. The weak acid takes its time, 1/10 of a millimetre here, 1/10 of a millimetre there, and in that slowness lies all the beauty. Patience is not a side effect of the process. Patience is the process. And now the part that is easy to walk past without noticing, the part worth slowing down for. The stone the water is dissolving is not really stone at all, not in the way we usually mean. Limestone is a drowned ocean. Almost all of it began as living things in a warm and ancient sea. The coral that built reefs, the shells of countless small creatures sinking to the seafloor when they died, the tiny calcite plates of algae, the minute, intricate skeletons of foraminifera, single-celled animals that built shells of breathtaking delicacy, raining down through the water for millions upon millions of years and settling in the mud below. Layer upon layer, body upon body, pressed and cemented over ages into rock. The grey hillside the rain is falling on tonight is the compressed graveyard of seas that vanished before the dinosaurs were ever born. So when the sour water carves a cathedral out of the limestone, it is hollowing out the remains of an ocean that has been dead for hundreds of millions of years, an ocean lifted up out of the deep, raised into the daylight, and now eaten away grain by the rain that falls upon its back. It is a strange thing to hold in the mind as you drift that the most solid rock beneath your feet was once soft, living water, and that the water falling upon it now is patiently turning it back into something that flows, stone becoming liquid, the sea returning in the smallest possible increments to the sea. If you find yourself somewhere in this story tonight, somewhere far away in the dark, with your own window and your own quiet, I would like to know where you are listening from. Leave it in the comments below if you feel like it, the name of the place where you are letting yourself fall asleep. And if you are new here and you would like more slow journeys into the deep and the old and the unhurried, you are welcome to subscribe and stay a while. There is no rush. There is never any rush down here. Tonight we are going to follow the water all the way down, from the first sour raindrop on the hillside to the largest rooms that exist anywhere beneath the surface of the world, and you are free to fall asleep at any point along the way. The water will keep going without you. That is rather the comfort of it. There is a word for this whole kind of landscape, the kind where the rain dissolves the rock, and the rivers run underground, and the surface is pocked and fluted and full of hidden doors. The word is karst. It comes from a high, stony plateau called the Kras on the edge of Slovenia. reaching across toward northeastern Italy, where this strange, dissolving terrain was first studied and described closely enough to earn a name of its own. The land lent its name to every limestone country in the world that behaves the same way, and there is a great deal of such country. Roughly a fifth of all the ice-free land on Earth is karst, or something close to it. A fifth of all the dry ground on the planet is quietly being eaten by faintly acid rain, and a comparable share of all the people alive drink their water from karst, from the springs and the hidden rivers and the flooded passages that the water itself has carved through the old sea. So this is not some rare curiosity in a far-off corner. It is happening beneath an enormous portion of the world, slowly all the time, including, very possibly, somewhere not far beneath wherever you are lying right now. Before the water disappears underground, before it goes down into the rooms it is making, it leaves its first marks on the surface, and they are worth pausing on. Where rain runs across a bare slab of exposed limestone, it does not stay neat and even. It gathers into thin trickles, and each trickle dissolves a little channel for itself, and over time the channels deepen into a delicate fluting, sharp-edged grooves and ridges running down the face of the rock like the folds of a curtain or the lines worn into an old step. The name for this fluted skin of dissolved stone is karen or lapies. To walk across a field of it is to walk across stone that the rain has combed, a whole hillside of grey rock, channeled and ribbed and slowly being thinned away by nothing more than weather and time. It is the surface writing down, in lines you can read with your fingers, exactly which way the water has been going. And then somewhere, the water finds a way in. A surface stream, running along quite ordinarily through the grass and the rock, comes to a place where the limestone has been dissolved enough to open a throat in the ground, and the whole stream simply pours into it and vanishes. One moment there is a stream. The next moment there is only the sound of water falling away into darkness, and a dry bed continuing on emptily downhill where the stream used to be. The place where this happens has a name too. It is called a ponor, or a swallow hole, and it is exactly what it sounds like. A place where the earth swallows a river whole. Stand at the edge of one and you can feel the cool breath of the underworld coming up out of it, and hear the water going down and down into a dark you cannot follow with your eyes, but the water can be followed, and we are going to follow it. Down beneath the ponor, beneath the place where the stream swallows itself and falls into darkness, there is a world that has its own geography, its own architecture, its own logic of space, and it obeys rules that are almost entirely different from the ones you know on the surface above. The first thing to understand about this underground world is that it is divided, not by walls built by any creature, not by intention, but by the position of the water table, that invisible horizontal surface, somewhere deep in the rock, below which every crack and cavity and dissolving passage is entirely full of water, and above which the passages are at least partly filled with air. This boundary, shifting over geological time as wet ages give way to dry ones and the land itself rises on the slow breath of tectonics, is one of the most consequential lines in the history of caves. Where you are in relation to it determines everything about the shape of the passage the water carves around you. Above the water table lies what geologists call the vadose zone. The name comes from the Latin vadosus, meaning shallow, though the irony is that the vadose zone can extend hundreds of meters down before it reaches the saturated rock below. What the name is really trying to capture is the quality of the water's situation here. It is unsaturated, moving through passages that still contain air, subject to gravity and gravity alone. There is no pressure pushing it sideways. There is no force sending it uphill. Water in the vadose zone falls, and it follows the steepest available path downward, exactly as water in any stream does, except that the stream is underground, and the banks around it are limestone. And because it falls and because it cuts downward. A vadose stream scrapes at its floor. Over time, and time here is not decades or centuries, but hundreds of thousands of years, the floor drops and drops again, and the passage that develops is tall and narrow, a slot in the rock, sometimes so tight a person turned sideways would barely fit between the walls, yet reaching 10 or 20 or 30 meters upward to where the ceiling closes in at the top. Carves call these canyons, and the word is not fanciful. They look exactly like river canyons, with undercut banks and polished walls and the smooth sculpted shapes of water-worn stone, except they are enclosed in rock on all four sides, and the only light is whatever light you brought with you. Below the water table lies the phreatic zone. Phreatic comes from the Greek phrea, a well, and the image is exactly right. The phreatic zone is a kind of underground well that has swelled until it fills every available space. Every crack, every joint, every passage that has been opened up by dissolution is completely and continuously flooded. The water here is not falling under gravity in the simple sense because there is nowhere for it to fall to. It is already at the lowest pressure available to it locally. Instead, it moves under the pressure of the water above and behind it, the weight of a whole landscape's worth of groundwater pushing it through the rock, the way water moves through a plumbing system in all directions, not just downward, toward wherever the pressure gradient leads it. And this change in the direction of the flow changes everything about the shape of the passage the water carves. In the vadose zone, the stream cuts its floor and leaves the walls and ceiling relatively untouched. In the phreatic zone, the water presses against every surface with equal insistence, floor, walls, ceiling, dissolving all of them at essentially the same rate because the acid-laden water is everywhere in contact with stone on every side. The result is a passage shaped less like a canyon and more like a tube, round or oval or smoothly lenticular. The cross-section of a phreatic passage has the gentle, continuous curve of something bored by a machine or shaped on a wheel, the curve of a water pipe or a tunnel through which a long, slow river of chemistry has been moving for thousands of years in absolute dark. Think of it this way: in the vadose zone, the water holds a chisel and cuts a slot. In the phreatic zone, the water is the water in a full bottle. It presses against the glass on every side with equal force. The glass here is limestone. The result is a round bottle of empty space, the water having dissolved the stone away from all its walls simultaneously. Cavers who have explored both kinds of passage know them instantly by feel even before they see. The phreatic tube is smooth and rounded and slightly eerie, like the inside of something cast, while the vadose canyon is raw and angular and goes up and up into darkness above your head. Now here is where it becomes more complicated and more beautiful. The water table is not fixed, it has never been fixed. Over the vast spans of time during which a cave system is developing, the water table rises when the climate is wet and the aquifer fills, and drops when the climate dries or when the land surface erodes down, and the springs, the places where the water escapes the rock and emerges at the surface, are able to drain from a lower level than before. And when the water table drops, the phreatic zone drops with it. The passages that were once completely flooded, those smooth round tubes shaped by water pressing from all sides, are now above the water table. They are now in the vadose zone. They are now in contact with air. And so a vadose stream, younger than the passage it now inhabits, enters this old, rounded phreatic tube and begins doing what vadose streams do. It cuts downward into the floor. into a floor that is already the curved bottom of a round tunnel. The stream cuts a narrow slot, a canyon within a cylinder, a groove beneath a dome. What you are left with when time has done its work and the caver's lamp illuminates the cross-section is a passage shaped rather like an old-fashioned keyhole. At the top, round and smooth, the phreatic inheritance, the ghost of the drowned passage. At the bottom, a narrow cleft with sharp walls cut into that curved floor, the vadose descendant, the younger and more impatient, water cutting its own signature into its ancestors' architecture. Cavers have been reading these keyhole passages for over a century, and every one is the same sentence written in stone. There was once more water here than there is now, and the water table has fallen, and the cave is draining, and time is passing at a pace you cannot quite hold in your head and still sleep easily. Up on the surface, meanwhile, the dissolution is working in ways you can see without going underground at all, and the vocabulary for what it does up there is worth lingering with a moment, because the landscape it makes is one of the most distinctive on Earth, and because every feature of it is connected through the slow descent of water to everything that is happening in the dark below. A doline is a closed depression in the surface of a limestone landscape. A hollow, a bowl, a saucer in the ground that the rain fills and that does not drain outward by any surface channel, only downward through the rock beneath it. They come in two kinds, and the difference between them is partly violent. A solution doline forms slowly over centuries or millennia as the limestone beneath gradually dissolves and the ground surface sags inward to follow it downward. It is gentler and more gradual, the Earth's equivalent of a mattress slowly losing its stuffing in one spot. A collapsed doline is something else. It forms when a cavity has developed near enough to the surface that the roof of that cavity becomes too thin and too weakened to support itself. And then one day, without warning or with very little, it fails. The roof falls in, the surface drops suddenly, and a hole opens that was not there before, sometimes meters across, sometimes much larger. People have built houses on ground that later collapsed into dolines. Roads have swallowed themselves. The ground in a karst landscape looks solid, and is solid until the moment it isn't. It is a landscape with hollow bones, and you cannot always tell from the surface which bones are there. Where several dolines have dissolved close enough to one another that their margins merge and run together, the compound hollow that forms is called a uvala. A uvala is not simply a large doline. It has the irregular, rolling, multi-lobed shape that comes from several dissolution centers combining like bubbles of acid, slowly merging on the face of the rock. In a landscape of uvalas, the ground has a rolling, sunken quality, dipping and rising in gentle curves that give no indication of the centuries of chemistry that produced each hollow, the millions of individual passages of water, each one leaving its grain of calcite dissolved, its molecule of stone carried away in solution to be delivered eventually to the sea. And then there are polies, a word from the South Slavic languages meaning field, and that is exactly what a polie is. A field. A vast, flat-floored, closed basin in a karst landscape, sometimes extending for several kilometers in each direction, with straight, steep walls rising from its flat floor on all sides, as if something very large and very flat has been pressed down into the landscape and then removed, leaving a neat impression behind. Polies are the great plains of the karst world. Some of them flood seasonally, filling with water in the wet season when the karst drainage system cannot absorb rainfall as fast as it arrives, then draining back underground as the dry season brings the water table down. A polie in flood is a temporary lake above a limestone sponge. And when the water drains, it drains as if through an invisible plug, the whole surface of the water lowering smoothly as the ponnas at the polge's floor open and let the accumulated rain back into the dark. The pores, those swallow holes, those places where the surface stream disappears, are where the story descends. They are the hinges between the surface world and the underground one, the doorways through which the slightly acidic water passes on its long journey through the rock. A stream can flow through many kilometres of ordinary valley collected from many hillsides, working its way down through soil and grass and gravel entirely conventionally, and then arrive at a ponner and vanish in a moment, traded from the world of light and wind and open sky to the world of narrow fissures and dissolving stone and absolute, permanent darkness. Tracking where the water goes once it passes through a ponner used to be a matter of guesswork and observation, following surface valleys and guessing which low ground the underground water might be feeding. But there is a technique that has, over the past century or so, made the invisible drainage of karst landscapes legible in a way that still seems slightly magical when you encounter it for the first time. You pour a dye into the water at a ponner, a fluorescent tracer, a chemical, rhodamine or fluorescein or similar, vivid green or orange in the right concentration, harmless to the rock and to the water. And then you wait. You station watchers at every spring and resurgence within a plausible distance, collecting water samples, holding the collected water up to ultraviolet light to see if the dye has arrived. And in time, it does. Sometimes hours later, sometimes days, sometimes a week, having moved perhaps 20 or 30 kilometers through the rock, following conduits and joints and dissolving passages entirely invisible from the surface, to emerge in a spring on a distant hillside with its color still detectably present in the water, fainter now, diluted by everything the aquifer has mixed into it. But there, the dye that left the ponor now arriving at the resurgence, the thread of connection drawn through solid rock and made, briefly, beautifully visible. A resurgence, a spring, is where the water returns. It has been in the dark, it has been in the rock, it has dissolved its passage through limestone over geological time and has been following that passage for days or weeks of its individual journey since it fell as rain, and now it emerges again into light and air, flowing from a cliff face or rising through gravel or welling up in a pool at the foot of a hill. The water that comes out of a karst spring has, in a sense, seen more of the interior of the earth than anything we normally encounter in daily life. It has been in the phreatic zone, pressurised and dark. It has passed through passages that took hundreds of thousands of years to dissolve, and it emerges clear and cold and tasting of stone, slightly harder than surface water, heavy with dissolved calcium bicarbonate that it will deposit slowly in the kettles and pipes and basins where it eventually rests. The same chemistry, the same equation run forward again in a new location, leaving the stone behind. Between the ponors and the resurgences, there are places in the cave where the underground passages move from air-filled chambers back into completely flooded zones, where the ceiling of the passage drops below the water table and the tunnel is entirely filled with water, impassable to any air-breathing creature without special equipment. These flooded sections are called sumps, and they are among the most consequential features in the geometry of cave exploration. A sump is a transition point between the vadose and phreatic worlds, a threshold where the air stops and the water takes over completely. Some sumps are short, only a few meters of flooded tunnel before the passage rises again above the water table, and there is air once more. Others are long. Some of the great cave systems of the world, systems with hundreds or thousands of meters of dry air-filled passage, are connected to one another by sumps that extend for kilometers of flooded conduit, explored only by divers who carry tanks of air on their backs and navigate by compass in water where the visibility may be only a few meters or zero. A sump is not an ending, It is a transition, the same geometry that a keyhole passage embodies, but in the temporal dimension. You are passing from the air-filled, surface-draining world above the water table to the pressurized, flooded world below it. The water does not know there is a sump there. For the water, the sump is just another section of the passage it has always been following. For a creature made of air and light and the need to breathe, a sump is a door that requires something extraordinary to open. It is worth pausing here for a moment, before we go deeper into the formations and the chambers and the deep time architecture of what water carves, to consider what it means that most of the world's limestone drainage is doing this entirely invisibly, not in surface rivers and open valleys, but in conduits in the rock, through ponors and along phreatic tubes and up again, at resurgences, an enormous subterranean plumbing system built over millions of years and carrying, at this very moment, a significant fraction of the water that humanity depends upon for drinking and agriculture. Roughly a fifth of all the land on Earth that is free of ice is underlain by karst or karst-like rock, and a comparable fraction of the world's population draws its fresh water from karst aquifers, from that slow, dark movement of slightly acidic water through limestone. The cathedral, as we will come to think of it, is also a reservoir. The most beautiful architecture in the geological world is also the plumbing. And then there is the version of this story that plays out not in gradual subterranean slow motion, but in the most dramatic possible surface form, in the places where the roof of a cave has collapsed and the water table is exposed directly to the open sky. In the Yucatan Peninsula of Mexico, the limestone sits flat and close to the water table. There are no significant rivers on the surface, no dramatic valley systems, no rivers flowing openly to the sea, because all the surface water disappears almost immediately into the limestone beneath it, swallowed by the karst and carried underground to the coast. The entire drainage of the Yucatan is subterranean, and the limestone is riddled with caves, with vast flooded passages connecting to one another in networks that extend for hundreds of kilometers beneath the flat, forested surface of the peninsula. Over time, in some places, the roofs of these caves have thinned and weakened and finally fallen in, not in the violent, sudden fashion of the worst collapsed dolines, but in the slow, inevitable way of stone that has been chemically thinned over thousands of years until one day the remaining thickness is not enough. When the roof falls into a cave whose passages are filled with water up to the water table, the collapse opens the cave to the surface and the water table is suddenly exposed, a pool of perfectly still, clear water at the bottom of a roughly circular shaft in the limestone, open to the sky above, surrounded by the broken walls of the cave that used to be there. This is a cenote. The word comes through Spanish from the Yucatec Maya word sonot, meaning something like a natural well, and wells are exactly what these pools functioned as for the people who lived above them. To stand at the edge of a cenote, and there are thousands of them on the Yucatan, from small jungle pools open to the blue sky through a hole in the forest canopy, to vast cathedral-like chambers flooded to their lip with water, is to understand the cave from a different angle. You are looking down through the hole that collapse made into the body of the cave that water made. The water below you is not a surface lake. It is the top of an entire underground world, a flooded network of passages extending in every direction beneath you, and for kilometre after kilometre in every direction you cannot see. The clarity of the water, clear as glass, cool, carrying in solution the same calcite the cave walls were made of, but not enough to obscure a visibility that sometimes extends for 30 or 40 meters before the blue-green dark takes over, gives the cenote a peculiarly architectural quality, as if you were looking through a window in the floor of the world into a cathedral submerged. The Maya understood cenotes as sacred places, and the understanding is not difficult to appreciate. In a landscape without surface rivers, the cenote is where water appears, still and deep and seemingly without source, welling up from inside the earth at the bottom of a stone shaft, with no explanation that would be visible to a person who had not followed the hydrology through centuries of observation. The water is there because it is the top of the aquifer, because the cave's roof has collapsed and exposed the water table. But to someone without that framework, the cenote is simply a place where the earth has opened and offered water from its own body. It is a gift from the underworld. In the great ceremonial centers of the ancient Maya world, cenotes were the sites of offerings, of rituals, of the passage between this world and whatever lay beneath it. Divers working in the cenotes of the Yucatan have found evidence of these offerings: jade, pottery, human remains, resting on the floors of passages that are now 30 or 40 meters below the water surface in the dark phreatic tunnels that connect one cenote to the next. And those tunnels are among the most extraordinary cave environments on Earth. The Sacaktun cave system and the Oxbelhar system, both in the Yucatan, are among the longest underwater cave systems so far mapped anywhere in the world, with hundreds of kilometers of surveyed flooded passage. And the survey is not finished. Cave divers have spent decades moving through these tunnels with lights and lines and the careful, measured economy of breath that underwater exploration demands, mapping the corridors and chambers and collapse features of an underground city of water and stone that the surface world above it gives no hint of. The flat, quiet, forested Yucatan sits above this drowned labyrinth without any visible sign of what is below. You walk across it on ordinary ground through ordinary trees, and there is nothing to tell you that beneath your feet the phreatic world extends through its rounded, smooth-walled, peacefully dark passages as far in every direction as the water table itself extends, which is to say, the entire peninsula. Some of the tunnels in the Sacaktun system still contain, above the waterline where ancient air pockets were trapped when sea levels rose after the last ice age flooded these passages again, formations on the walls and ceilings, stalactites, flowstone. The unmistakable record of a time when these passages were above the water table, when they were air-filled caves, and when the same chemistry of degassing and precipitation that builds decorations in every limestone cave was at work here in the dark. The sea level rose, as it has done many times as ice ages end and glaciers melt and the oceans rise to fill the space, and the air-filled cave was flooded. The stalactites that were forming, growing their 1/10 of a millimetre each year, were drowned. They are still there, submerged, the water around them clear enough to see by the light a diver carries, hanging from a ceiling that is now underwater, stopped in the act of growing, as still and as patient as everything else in this story. The sea rose. The chemistry paused. The formations wait, and so the water's journey from the panor on the surface to the phreatic conduit below, from the collapsed doline to the cenote and the flooded passage, is in all its forms a single continuous process, the slow trade of rock for space, carbonic acid for calcium bicarbonate, surface for depth. The water is always going somewhere, it is always doing the same thing, and the cave is not a destination, not a place the water is trying to reach. The cave is simply the shape that the water leaves behind, the space that opens in the limestone in the wake of the chemistry, the room that was not there before the water arrived and that will continue to grow imperceptibly for as long as the water continues to move through it. It is the absence that acid makes. It is the shape of dissolution. And what fills that shape? What decorates the absence? what turns the empty carved room into something that early explorers reaching it by torchlight immediately, instinctively called a cathedral, comes from that same water, doing the same thing in the same darkness, but running the equation the other way. The water that has dissolved its passage through the limestone is carrying, as it travels, everything it has taken from the rock. It is carrying calcium bicarbonate in solution, the former stone dismantled molecule by molecule and held in the water the way salt is held in seawater, invisible, perfectly dissolved, present but weightless. It will carry that dissolved stone indefinitely as long as conditions stay the same. But conditions do not stay the same. At the edge of the air-filled cave, something changes. The cave's atmosphere has less carbon dioxide in it than the water does. The water, remember, has been carrying carbon dioxide in solution since it passed through the soil, and it has been holding a concentration of carbonic acid that the still air of the cave cannot match. And so the water degasses. Not dramatically, not in bubbles or foam or any visible rush. Quietly, at the molecular level, the carbon dioxide that was dissolved in the water moves from the water into the cave air, because moving from where it is more concentrated to where it is less concentrated is exactly what dissolved gas does. The same impulse that spreads perfume through a room, the same impulse that lets cream swirl through coffee, carries the CO2 from the water into the air of the cave. And when the CO2 leaves the water, the carbonic acid, which was CO2 dissolved in water, is no longer there. The equation that had been running forward, dissolving limestone, can no longer run forward. It runs backward instead. The calcium bicarbonate that was comfortably dissolved in water rich with carbonic acid is suddenly in water that is no longer acidic enough to keep it dissolved. So it comes out of solution. It precipitates. It finds the nearest solid surface, a crack in the ceiling, a roughness in the wall, the rim of a pool, and it deposits there a tiny, invisible film of calcite, so thin you could not see it with the naked eye, so thin that 100 of these films laid one on top of the other would be about a millimetre. And yet this is how the cave gets dressed. This is where the stone comes back. The same rock that the acid took from the limestone above is set down again, layer by invisible layer, in the cave below. We are following the water to where this happens. We are descending still through the dark. And what waits below is the cathedral, building itself in the silence, one unphotographable layer at a time, for longer than our kind has been alive to wonder at it. The cenotes of the Yucatan stay with us for a moment longer before we go, because they hold one more piece of the story that wants to be said here, at this threshold between the surface world and the world of formations. They were not only sacred, they were also, in the simplest and most practical sense, how a civilization survived in a landscape where no rivers ran. The same geological accident that made them visually extraordinary, the collapse of a cave roof, the exposure of the water table, made them functionally essential. The water in a cenote is the water table. It is the phreatic zone exposed. It is the same water that is moving slowly through the Sac Acton and Oxbelhar passages far beneath the surface, the same water that arrived as rain and passed through Penors and followed the dissolving conduits through the rock. In a sense, a cenote is simply a cave that has been opened by its own success. The chemistry worked so long and so thoroughly on the cave roof above the water table that the roof became too thin to stand and the sky got in. And where the sky gets in, people can get down, and where people can get down to water, people can live. The Cathedral of Dissolution was, in the Yucatan, also a well, also a home, also a place where the living and the dead were brought to the edge of the underground world and offered into its keeping. There is something to sit with in that. The the same patience that carves the passage, that rounds the phreatic tube and cuts the vadose canyon and opens the doline and dissolves the polge floor. That same patience provides. The same geology that makes the landscape above strange and pitted and hollow makes the water below available and clear. The dissolution that seems like loss from above is abundance from within, and we are going deeper into that abundance now, down through the levels of the cave, past the junction of the vadose and the phreatic, past the keyhole passages and the ancient tubes and the newer slots, past the sumps where the air ends and the dark water begins, into the chambers where the equation has turned itself around and the stone is coming back, 1/10 of a millimetre at a time, in formations that grow with a patience so extreme it becomes its own kind of peace. Think about what has just happened for a moment. Think about the direction of it. For everything we have followed until now, the water has been a thief. It stole carbon dioxide from the open air and stole more, far more, from the breathing soil, from the rotting leaves and the roots going about their slow underground labor. It carried that theft downward as carbonic acid, weak but persistent, and it gave the acid to the stone, and the stone, over time, gave way. Calcium carbonate, the mineral that built the shells and the coral and the plating of 1 billion marine creatures across seas that no longer exist, dissolved into calcium bicarbonate and was carried off in solution, passage by passage, century by century, into the rivers and eventually the sea. The water took, the rock surrendered, the space opened. That has been the story until now. But here, in the deeper chambers, in the sections of the cave where the air is still and the dark is absolute and the sound, if there is any, is only the soft and metronomic sound of a drip, here the direction of the story reverses. The same water, the same equation, the same atoms of calcium and carbon and oxygen that were taken from the stone above. They come down through the ceiling, one drop at a time, and they give back. They set the stone down again. They build. The mechanism is almost absurdly simple. The water arrives saturated. It has dissolved as much calcium bicarbonate as it can hold, given the concentration of carbon dioxide it was carrying when it moved through the rock. But the air in the cave is different from the air in the soil. The soil air, remember, holds 10, sometimes 100 times as much CO2 as the open atmosphere. That is where the water found its acid in the first place. The cave air holds much less, and so the water, arriving at the cave ceiling with its load of dissolved calcium bicarbonate, encounters an atmosphere that cannot hold the carbon dioxide it is releasing. The CO2 moves from the water into the cave air, and the moment it does, the equation shifts. The same equation that read, going forward, as dissolution now reads in reverse. Calcite, calcium carbonate, precipitates. A tiny amount of it from each drop, an amount almost impossible to see with the naked eye and entirely impossible to feel, but it is real, and it is there, and it does not stop. What is happening, in the most precise sense, is that the water is breathing out. Going through the rock, it breathed in. It absorbed the carbon dioxide, it became the acid, it dissolved the stone. Now, hanging at the cave ceiling in a drop smaller than a garden pea, it breathes out. The CO2 escapes into the still cave air. The calcite it was carrying, because calcite was what it had borrowed, calcite was what it dissolved, can no longer remain in solution, and so it leaves the water. It takes solid form. It crystallizes in a ring, in a film, in a layer so thin that even the word thin seems too coarse. It becomes stone again. The carver is the decorator, the solvent is the cement. The process that made the hollow is the process that fills the hollow with wonder, and the difference between the two is nothing more than the direction a breath of carbon dioxide chooses to travel. This is the reversal that makes a cave into a cathedral, not violence, not heat, not pressure in the geological sense of crushing and contorting, just a change in the air and a molecule of gas moving from a place of higher concentration to a place of lower, the way all gases do, following the most ordinary physical law there is, and in doing so, making something that looks as though it required a divine plan. The word that covers everything built in this way, or everything that grows by precipitation of calcite or related minerals from solution onto cave surfaces, is speleothum. It is the umbrella, the genus, the name that takes in all the forms before they are distinguished, speleothum, from the Greek for cave and deposit. And within that family, the forms are many. But there is a sequence, a kind of biography, that is worth following from the beginning, because the beginning is very small. The beginning is a single drop hanging from the ceiling in the dark. There is a useful shorthand, a small piece of memory work for distinguishing two of the most common speleothems from each other. Stalactites hold tight to the ceiling, the C in stalactite for ceiling. Stalagmites grow from the ground, the G in stalagmite for ground. It is perhaps too neat, too much like a school exercise, and yet it is precisely true. And if you know those two words and can hold them in mind, then everything else the cave builds can be located around them, either joining them or departing from them in some direction. But neither of them begins as what they eventually become. They begin as something far more delicate. They begin as a soda straw. Stand beneath a cave ceiling in your mind, a limestone ceiling, dark, damp, ancient. A drop of water is forming there. It emerges through a tiny pore or fracture, and it gathers and grows, and it hangs. And even as it hangs, before it has fallen, it is degassing. The CO2 is moving out of the water and into the cave air. The calcite is precipitating, and it precipitates exactly where the water is, at the outer edge of the drop, where the water meets the air. This leaves a ring of calcite, a ring the exact diameter of the drop, roughly 5 millimeters. And then the drop falls and another forms in the same place, and another ring of calcite is added below the first, because the new drop hangs from the old ring, and it too degasses and it too precipitates, and then it falls and another comes and another ring is added. Each ring is tiny, but each ring is attached below the last. And what grows over time, very slowly, at the pace we will come to in a moment, is a tube. A hollow tube, open at both ends with walls the thickness of a single calcite film and an internal diameter of roughly 5 millimeters. It is exactly the shape and the inner diameter of the straw you might use to drink something cold on a warm day, and so it is called a soda straw. And it is, in its early life, precisely that. A thin, fragile, hollow tube of stone hanging from the ceiling, water moving through it along its inner canal, carrying the dissolved calcite to the hanging tip, where the next ring is added. Soda straws are extraordinarily beautiful and extraordinarily fragile. They are also, in the right conditions, extraordinarily long. The longest known undisturbed soda straws exceed 6 meters in length, roughly the height of a 2-story building, measured from ceiling downward. A single hollow tube of calcite, the width of a drinking straw, hanging in the dark over what may be millions of years of incremental growth. To see one intact is a kind of privilege, because they break easily. A disturbance in the air, a vibration carried through the stone, a careless motion in the passage. Any of these can shatter a soda straw that took 10,000 years to grow, because it is, at its wall, almost nothing. A shell of mineral, a fraction of a millimetre thick. Most of them do not stay straws. The canal is very narrow and eventually it clogs. A mineral particle too large to pass, a tiny blockage of some kind, and the water can no longer move along the inner path. It moves instead along the outside. It runs down the outer wall of the tube, still carrying its dissolved load, still degassing at the surface, still precipitating calcite, but now depositing it on the outside rather than adding a ring to the tip. And the structure thickens. The fragile hollow tube begins to fill and to widen and to take on the shape we more often picture when we think of this form, the carrot shape, the tapering solid cone that is thicker at the ceiling and narrows toward the tip. The stalactite we recognize has grown out of the soda straw it once was, the inside filled, the outside built. The whole thing slowing even further as it widens because now the surface over which the water moves is greater and each drop is spread more thinly and each increment of calcite is spread more broadly, and the growth rate, already very slow, slows further still. And how slow is very slow. This is where the scale becomes, if you let it, a kind of comfort. A stalactite grows at roughly 1/10 of a millimetre per year. 1/10 of a millimetre is approximately the thickness of a human hair. In a year, 365 days, 12 full seasons, a summer and a winter, and another summer, and another winter, and another. The stalactite adds approximately the thickness of a hair. To add 1 full centimetre, it needs roughly a century. To add the length of your hand, let us say 20 centimetres, it may need 2,000 years. 2,000 years ago, in a cave in the heart of whatever continent you care to imagine, a stalactite was 20 centimetres shorter than it is now. It has been growing through every revolution of human civilization above the surface at the speed of a growing fingernail, in absolute darkness, in a silence broken only by the sound of the drops that were adding to it, one hairbreadth at a time. The cathedral is not built quickly. The cathedral has no deadline. The cathedral does not know it is a cathedral. It is the natural consequence of an equation pursued with perfect patience by the laws of chemistry in the dark. While the stalactite descends from the ceiling, the drops that form it eventually fall. They fall to the floor of the cave, and when they arrive, they still carry some of their dissolved load. Not all the calcite has precipitated at the ceiling, and the impact of landing disturbs the water further, and more CO2 escapes, and more calcite is deposited. It is deposited on the floor. It builds upward, not a tube, not a hollow straw, because the water is not hanging and forming a ring, but splashing and spreading. So the deposit is a mound, a dome, a column that widens toward the base. A stalagmite grows from the ground. It grows more slowly, in general, than the stalactite above it, because it receives only the calcite left over after the ceiling has taken its share. But it grows, and the two of them, the stalactite descending, the stalagmite ascending, are growing toward each other, though neither knows it, over time scales that make the word slow seem almost flippant. When they meet, they become something else. When the tip of the descending stalactite and the summit of the ascending stalagmite finally touch, not a dramatic collision, but a moment of contact that has been approaching for perhaps hundreds of thousands of years, they become a column, a pillar. The join is often visible, a slight change in the crystalline texture, a line where two separate growth histories became one continuous structure. The column stands from floor to ceiling, or nearly so, a closed circuit of stone that carries the full record of the water that built it. Every change in drip rate, every shift in climate above the surface, every variation in the CO2 content of the soil through the seasons, all encoded in the concentric layers of calcite that can be read, if you know how, like pages of a book. But not all the water reaches the cave as a single drip from a single point. Some of it arrives as a film, where water seeps through a slope of rock and emerges not at one concentrated fracture, but across a broad surface, it flows as a thin sheet down the wall or across the floor. And where a thin sheet of calcite-saturated water flows, it deposits a thin sheet of calcite. Layer by layer, over time, these sheets build up. They smooth over the irregularities of the cave surface. They follow the contours of the wall, conforming to every curve and hollow. They drape the rock the way cloth drapes a form, with fidelity, with softness, with the appearance of something flowing even though they are perfectly rigid. This is flowstone, and it can cover entire walls and floors in sheets of calcite that are themselves layered, the layers reflecting every change in the rate of flow over the centuries, every hiatus when the water above dried up and deposition paused, every renewal when the rains returned and the water came back to add another coat. Flowstone looks like frozen waterfall, or like something poured by a careful hand and allowed to set, the shapes too organic for masonry and too regular for chaos. Where the water moves across a relatively flat floor and pools behind low ridges, something related happens. Calcite precipitates at the edge of the pool, specifically at the surface of the water where the CO2 escapes most readily, and builds a low dam, a rim, a crescent of stone at the water's edge. The dam holds the pool. The pool grows behind the dam. More calcite deposits at the new water line. The dam grows taller, and behind it the water is held in a still basin, and in the still basin more calcite may deposit on the basin floor. These dams are called rimstone dams, or by the French-derived term gours, and they terrace the cave floor into a series of shallow pools like steps in a garden or like rice paddies seen from above, each step holding its still water, each edge a clean white rim of stone. They are among the most serene structures in any cave. In some chambers, they cover the entire floor in an architecture of basins that has no parallel in anything built by human hands, and yet looks unmistakably designed. And then there are the helictites. Everything described until now has obeyed gravity. Stalactites hang down because water hangs down before it drips. Stalagmites build up because that is where the drops land. Flowstone follows the slope. Rimstone dams follow the waterline. Gravity is present in all of it, directing the water, directing the deposit. But in the helictites, gravity seems to have been overruled. They are speleothems that grow sideways and upward, and in curves and in spirals, and in directions that have no obvious relationship to which way is down. They extend from cave walls and ceilings at angles that range from oblique to nearly horizontal, to occasionally pointing upward. Some curve back on themselves, some twist in helices, which is where the name comes from, some branch. Some look in the lamplight like the antlers of an unknown creature, or the roots of a plant growing in some medium other than soil. They are not large, usually. A few centimetres is common, they rarely exceed half a metre. But the incongruity of their direction, their refusal to comply with the organising principle that has governed everything else in the cave, makes them extraordinary. They are the formations that make experienced cavers stop. The explanation for them has not been fully settled, which is itself worth noting. The prevailing idea is that in a helictite, the water moves not along an outer surface where gravity can direct it, but through an internal capillary, a channel so fine that surface tension and the forces operating at the scale of crystal growth are stronger than gravity. The water does not run, it seeps at a pace so slow that each new crystal can form in whatever direction the existing crystal lattice inclines it toward. The crystal grows the way a crystal grows, following its own geometry, and the water follows the crystal, not the other way around. So the helictite goes where the calcite structure leads it, rather than where water would fall if left to its own inclinations. That is the theory, or the most widely held version of it. There are others. There is still, in the scientific literature, some genuine uncertainty about the exact mechanism. And there is something fitting about that, the cave that was carved by a process as simple and ancient as weak acid and soluble rock has decorated itself, in places, with formations that resist a tidy explanation. The helictite is the cave's refusal to be entirely legible. It is the formation that says, the story is not quite as simple as you thought. There are other formations that push into the stranger corners of what is possible here. Cave pearls, for instance. They are named for what they resemble, and the resemblance is very close. Where water drips into a shallow pool with some regularity, and where the pool contains a small grain of something, a sand particle, a fragment of bone, a tiny piece of the cave ceiling that has fallen, the dripping water keeps that grain in motion. Not violent motion. A gentle, intermittent agitation, the grain shifting and rolling with each small disturbance of the water surface. And around that rolling grain, calcite precipitates. It coats the grain on all sides because the grain is tumbling and presenting all its surfaces in turn to the supersaturated water. The layers build up concentrically, each one conforming to the smooth outer surface of all the layers before it, until the grain at the center is buried in a sphere of calcite that has been polished smooth by its own constant motion. The result is a ball of stone that is round and pale and smooth and often lustrous, and sits in the pool the way a pearl sits in an oyster. In some pools they occur in nests of dozens or hundreds, pale spheres of varying sizes crowded together on the pool floor, each one the record of a single grain's long tumbling life in the dark water. There are the draperies, sometimes called curtains. They form on inclined surfaces, ceilings that slope, walls that lean, where water flows down the incline as a thin film and deposits calcite in a continuous, slightly undulating sheet. As the sheet grows, it takes on a translucency in thin sections where the calcite layers are fine and relatively pure, and in those thin sections the mineral stains from the overlying rock, traces of iron, of manganese, of other compounds carried down with the water, show through as bands of color. Brown, rust, cream. The banding runs parallel to the direction of flow, and the pattern is strikingly similar to a particular kind of cured meat, which is why cavers have given these formations an informal name that the guidebooks sometimes use without apology: cave bacon. It is not a dignified name for something that may be 100,000 years old and grows in the permanent dark, but it is accurate. Moon milk is different from all of these in texture, and it has a strangeness that the harder formations do not. It is a white, soft, paste-like material found coating walls and floors in some caves, damp and smooth to the touch. It is composed of very fine crystals of calcite, or sometimes of other carbonates, magnesium-bearing ones, that have grown in conditions where rapid crystallization produced a powdery, high surface area aggregate rather than the dense solid of a stalactite. Where the chemistry is right, and the humidity is high, and the drip rate and CO2 gradient combine in a particular way, the calcite does not organize itself into the orderly columns of a stalactite, but into a soft mat of microscopic needles. The result is something that looks as though it has been applied with a brush, or grown by something biological, and for a long time there was genuine uncertainty about whether it was a purely mineral formation or whether microorganisms were involved in its production. The current understanding leans toward primarily mineral, but in many moon milk deposits microorganisms are present, and their role is not entirely dismissed. It is another place where the cave's story resists a clean ending. There is also a formation called coralloid, or popcorn, a name that describes its appearance exactly. Knobby, rounded, clustered projections that coat surfaces in irregular masses, looking like something between cauliflower and the coral of a reef. They grow in a variety of ways, from films of water wicking across a surface, from condensation where moist cave air meets a cooler surface, from spray near a subterranean waterfall. They are among the more common cave coatings in passages where the air moves and the humidity fluctuates, and they give cave walls a texture that is neither smooth nor jagged, but something in between, something organic-looking that the geometry of dissolution would not on its own produce. And all of these together, stalactite, stalagmite, column, soda straw, flowstone, rimstone dam, helictite, cave pearl, drapery, moon milk, coralloid, all of these go under the single umbrella word speleothem. They are the decorations of the cave, all built by the same fundamental process. Water arrives in the cave carrying more calcite than the cave's air will allow it to hold. It releases carbon dioxide. It deposits calcite. It does this everywhere the chemistry is right and the drip geometry is particular to the surface. The variety of forms produced by those variations in drip and surface and CO2 gradient and mineral content is the variety that fills a cave with its own architecture. And that architecture is the accumulated record of water's slow, patient, invisible labor in the dark, over timescales that make the history of any civilization seem like an afternoon. Consider what 1/10 of a millimetre per year means across 100,000 years. In 100,000 years, a stalactite growing at the average rate adds 10 meters to its length, 10 meters in 100,000 years. The tallest stalactites ever measured exceed the height of a 4-story building, and they have had, in the great cave systems, time enough to reach those heights. Time is the only resource the cave has in abundance. Everything else, the water, the CO2, the calcite, moves through in small quantities and at low rates. But time is inexhaustible in the dark, and a process that works at the scale of a hair's thickness per year can, given enough time, produce something that stands as tall as a building and as wide as a tree trunk in a room large enough to dwarf any cathedral built by human hands. The rate is not constant. This is important, and it opens one of the more remarkable things about what a stalagmite is. The growth rate varies with the conditions above the surface. In a wet period, a century or a millennium of higher rainfall, the water reaching the cave carries more carbonate, the drip rate is higher, the supersaturation is greater, and the growth is faster. In a dry period, the drip rate slows, perhaps stops entirely, for seasons or years, and the growth slows or pauses. The boundary between a fast layer and a slow layer, or between deposition and hiatus, is preserved in the calcite as a change in texture, or in the density of the crystal layers, or in the trace mineral content. The ratio of different isotopes of oxygen, for instance, which reflects the temperature and the source of the rainfall. These are the pages. The stalagmite is the book. And because the calcite contains trace amounts of uranium, and uranium decays to thorium at a known rate, the age of any particular layer can be measured with precision. Uranium-thorium dating, sometimes abbreviated to UTH dating, reads the clock that the calcite itself contains. It can reach back hundreds of thousands of years with reliable results. Researchers have taken stalagmites from caves around the world and sliced them open and read their layers the way dendrochronologists read tree rings, and the records they have found cover ice ages and interglacials, wet epochs and dry monsoon shifts and drought cycles, all encoded in concentric pale rings of calcite built up in darkness at 1/10 of a millimetre per year, while the surface above went through every kind of weather and crisis and transformation. A single stalagmite can be a climate archive reaching back further than our species has existed in its current form. And it is sitting in a cave somewhere, growing, adding its hairbreadth layer every year in the dark. Not recording, exactly. It has no intent. But accumulating the way all patient things accumulate, the way the cave accumulated its passage, the way the limestone accumulated its shells, the way the sea floor accumulated the creatures that would eventually become the rock that would eventually be dissolved by the rain and deposited as the stalagmite that records the rain that dissolved the rock that was once the sea. The circle is long. It is very, very long, but it is a circle. The speleothems are growing in the dark right now. Every hour, in every cave, in every karst system, on every continent, the drops are falling and the calcite is precipitating and the formations are adding their invisible increment. We are not there. We would not be able to see it if we were, because the rate of change is far below the threshold of human perception. But it is happening. The soda straw is slightly longer now than it was when this narration began. Not by any amount that could be measured with ordinary tools, but it is longer. The stalagmite is fractionally taller. The flowstone has added a molecule's worth of new calcite to its smoothly draped surface. In the cave, the equation runs backward without pause, with the same unargued inevitability as gravity and the same unhurried pace as deep time. It has been running for as long as there have been caves in the limestone. It will run for as long as the limestone lasts. There are chambers somewhere in the dark below us. Chambers that are the product of all this, carried to a scale that is difficult to hold in the mind while remaining comfortable in a bed. Chambers where the stalactites have had millions of years to grow and have used them. Chambers where the flowstone has covered everything, the walls, the floors, the breakdown boulders, in a continuous coat of pale calcite that gives the whole space the appearance of having been sculpted from a single material, the jagged and the smooth unified under the same skin. Chambers where the columns stand so numerous and so close that walking between them would require turning sideways and navigating by feel. Chambers where the cave pearls lie in nests on the pool floors, and the rimstone dams step the water down through a series of still basins towards some deeper passage, and the helictites emerge from the walls in all their gravity-defying variety, and the cave bacon hangs from the sloping ceiling in thin, translucent sheets banded with rust and cream. We are heading toward those chambers now. We are heading toward the scale. The great rooms. The ones whose dimensions require comparison to things we know from the surface world, because the numbers alone do not carry the meaning. We are heading toward the caves that make the word vast feel adequate and then make it feel insufficient. But we go there slowly. The cave requires it. The cave has always required it. Patience is not a virtue here. It is the only pace. The dark ahead of us is the same dark the water has been moving through for a very long time. And it has been busy in that dark. It has been building. And so we arrive, at last, at the great rooms. Not as a reward exactly. The cave does not give rewards. It gives revelations, and slowly, but as the natural consequence of following the water long enough. Down through the soil where it borrowed its acid from dead leaves and root breath. Down through the Karen-fluted surface where it found its first limestone and began, in its imperceptible way, to ask the rock to step aside. Down through the Pona where the stream gave up its surface life and entered the dark willingly. Through the Vadose canyon, cutting its tall, narrow slot downward, and then the phreatic tube, rounded and pressurized and patient, dissolving in every direction at once. And then, in this part of the story, the water has been doing this for a very long time, not centuries, but millions of years. And the result is waiting in the dark ahead, and it is enormous. The Sarawak Chamber sits inside a cave complex called Gua Nasib Bagus, which translates simply and perfectly as Good Luck Cave. It is in Gunung Mulu National Park, in the Malaysian state of Sarawak, on the island of Borneo. The name of the park and the name of the cave system and the name of the island itself are worth saying quietly and letting them settle. Borneo, a word that carries weight, that suggests antiquity and distance, and the deep interior of somewhere genuinely wild. And beneath that island, inside a mountain of limestone, there is a room. The room is approximately 700 meters long and approximately 400 meters wide and at least 70 meters high. Those numbers are significant on their own, but they do not do quite enough work until you pair them with something familiar. If you were to take a fleet of Boeing 747 aircraft, full-sized, wide-body, among the largest commercial aeroplanes ever built, and park them on the floor of the Sarawak Chamber, nose to tail, you could fit dozens of them inside with room left over. Not a few, dozens. The floor area is so great that the far walls, in any light a human explorer could carry, would be lost in the dark. You would not be able to see from one end to the other. You would be able, in a meaningful sense, to get lost in the distance of a single room. A team of British cavers surveyed it in 1981, which is recent history by any measure, well within the lifetime of many people listening to this now. The cave itself is incomprehensibly older. The room was not made in 1981, it was found in 1981, which is a different thing entirely, and an important one. It had been here, in the dark, growing slowly larger as the limestone dissolved around it, for an enormous stretch of time before any human eye encountered it. The survey team's torches were the first light the Sarawak Chamber had ever known. The rock walls had been dissolved in total darkness. The floor, which is a chaos of enormous breakdown boulders, limestone slabs that fell from above as the roof opened and widened over geological time, had been lying there in absolute quiet. Not in geological time, which is a phrase we use loosely, in actual, literal darkness and silence for what we must honestly call ages. The Sarawak Chamber is the world's largest known cave chamber by area. It holds that title currently with the caveat that cave exploration is ongoing, that the deep limestone regions of Southeast Asia and China remain only partially mapped, and that it is genuinely possible, perhaps likely, that larger rooms exist and are simply waiting, which is itself a remarkable thought to carry gently into sleep, that somewhere beneath an unvisited mountain there may be a room larger than the largest known room, and neither you nor anyone else has yet stood in it. In the Guizhou province of China, in a cave system called Gabihe, there is a chamber named the Miao Room. It challenges the Sarawak Chamber not in area, but in volume, the total cubic measure of empty space inside it, and depending on how measurements are taken and verified, it sometimes holds the title of the world's largest cave chamber by volume. The debate between these two rooms, Sarawak by footprint, Miao by cubic volume, is a quiet, technical one among cave surveyors, conducted with measuring equipment and careful triangulation in places where no measuring equipment was ever expected to go. Both rooms are staggering. The distinction between them is a little like arguing which ocean is larger while standing on the shore of both simultaneously. These chambers were not built. That word belongs to bridges and cathedrals and the things humans make by adding material and intention. These rooms were subtracted. They were created by the removal of matter that was once here and is no longer here, carried away grain by grain, ion by ion, dissolved into water and transported invisibly through the rock and eventually released somewhere at a spring, into a river, into the sea, as calcium bicarbonate in solution, returning at last to the ocean that the limestone itself once was. The room is the absence left behind by a former ocean, slowly recalled home by rain. And the water did not stop at the great rooms of Southeast Asia and China. In the hills of Kentucky in the United States, there is a cave system that has been explored, mapped, and extended continuously for well over a century. And it remains the longest known cave system in the world, Mammoth Cave. More than 686 kilometers of surveyed passage, and that number has been revised upward repeatedly over the decades as new connections are found, as cavers push through tight crawls and emerging sumps and previously impassable sections, and the map grows. It is the longest cave system on Earth by a considerable margin, and it too was carved by the same weak acid, the same carbonic acid dissolution, the same slow removal of limestone from an ancient sea floor that had been lifted over vast geological time into the hills of what is now the American Midwest. The passages of Mammoth Cave are not all cathedral-scale rooms. Many of them are low, horizontal tunnels, the characteristic flatness of phreatic dissolution at an ancient water table. And some of them are tight and unromantic and require careful navigation. But the system contains large spaces too, and its sheer linear extent creates a different kind of wonder. Not the wonder of a single enormous room, but the wonder of interconnection, of the way water, given enough time and enough limestone, builds not a room, but a city. A sprawling, multi-level, intersecting network of passages that reflects the entire drainage history of the region above it, layer by layer, ancient water table by ancient water table, going back millions of years. Go deeper now, not in length but in depth, and you reach another set of superlatives entirely. In the country of Georgia, in the Caucasus Mountains, there is a massif called the Arabica Massif, and within it are two cave systems that, between them, hold the records for the deepest known caves on Earth. The Krubera Cave, sometimes called Voronya, which means crow, and Veriovkina Cave. Veriovkina has been surveyed past 2,200 meters of vertical depth. That is 2 kilometers and more, straight down through the mountain, following passages that descend through vadose shafts and phreatic sumps, and more vadose canyons in alternating sequence. The cave's architecture, a record of every fluctuation in the water table and every period of glacial or interglacial pressure, change across the millions of years the mountain has existed. To descend Veriovkina requires not a walk, but an expedition. Ropes and camps and diving equipment for the sumps, the flooded horizontal passages that must be passed through underwater to reach the next air-filled section. Cavers who have reached the deepest explored points in these systems have taken days to get there and days to return. 2,200 meters. The weight of rock above you at the deepest explored point is substantial enough that it is, in a sense, a different world down there. In temperature, in pressure, differential in the water, in the age of the passages, in the particular character of the darkness. And yet the cave that created this depth is, in its mechanism, perfectly continuous with the cave beneath any karst hillside. The same weak acid, the same reaction, CO2 and water and calcite. The difference is only time and geometry and the particular faulting of that specific mountain, the particular angles at which the rock tilted and fractured to give the water its path downward. And then there is Son Jong. In the Phong Nha Ke Bang National Park of central Vietnam, there is a cave passage, one passage, a single cavern segment within a larger cave system that is so large it contains, within itself, features normally reserved for the surface world. Son Joong has, in sections where the cave ceiling has collapsed and created skylights, great vertical shafts of daylight falling in from above, where breakdown dough lines have opened to the sky. A jungle, an actual jungle, growing on the cave floor, watered by rain falling through the skylights and nourished by the sudden column of sunlight in an otherwise lightless space. The trees reach toward the opening above them. There is moisture enough to produce at certain times clouds, wisps of water vapor forming and dissipating in the enormous air column of the passage. Son Jong contains sections large enough that a city skyscraper, stood upright on the cave floor, would not reach the ceiling. It is, in certain sections of its length, a world rather than a cave. It was not widely known to the outside world until relatively recently, properly surveyed by joint British-Vietnamese teams beginning in 2009, though local people in the region had known of its entrance for years. It is, as the Sarawak Chamber is, a discovery that changes the sense of what is possible underground. Each of these places revises upward, quietly, the ceiling of imagination. Now hold all of those rooms. The Sarawak Chamber in Borneo, the Miao Room in China, the 686 kilometres of Mammoth Cave in Kentucky, the 2,000-metre depths of the Arabica Massif, the jungle-bearing passage of Son Jong. And then add this. They were all, every one of them, made by water. Soft water, carrying a weak acid borrowed from soil and decomposing leaves. The same water that falls on your roof on a rainy night. The same chemistry that runs across a limestone pavement and cuts shallow flutes you could brush with your fingertips. It is the same process, only the time changes. And the time in these great systems has been vast. There is, however, a complication, a genuine twist in the story that the textbooks took a long time to accommodate, and that changed, when it became clear, a significant piece of what geologists thought they understood about how great cave systems form. Not all of the world's most beautiful and most decorated caves were carved by carbonic acid falling from above. Some of them were dissolved from below, and by a different acid entirely. Carlsbad Caverns in the Guadalupe Mountains of New Mexico in the United States is among the most visited caves in the world and one of the most dramatically decorated. Great banks of stalactites, extraordinary draperies, formations of unusual complexity, and variety-filling chambers whose names, the Big Room, the Hall of Giants, tell you something about the scale that greeted the people who first explored and named them. And for a long time, the assumption was that Carlsbad had been formed more or less as other limestone caves are formed, by carbonic acid percolating down from the surface, dissolving the limestone from above. That assumption turned out to be wrong. A few tens of kilometers from Carlsbad, there is a cave called Lechuguilla. It was long dismissed as a dead end, a shallow cave with an impressive entrance room and then a passage that seemed to stop, blocked by rubble and debris. In 1986, cavers began moving that rubble, following a persistent outward draft of air that suggested open passage on the other side. What they eventually broke through into rewrote the science. Lechuguilla was enormous and deeply and unusually decorated, but more importantly, it was formed by a process that was the near opposite of what most limestone caves experience. The limestone of the Guadalupe Mountains contains, in the rock below the cave zones, deposits of oil and gas. Hydrogen sulfide, the gas that smells of rotten eggs, doubtlessly was rising through the rock from those deposits, and where it encountered oxygenated groundwater near the cave zones, a chemical reaction occurred. The hydrogen sulfide was oxidized to produce sulfuric acid, not carbonic acid, with its gentle borrowed CO2, sulfuric acid, a genuinely strong acid compared to which carbonic acid is almost polite, and one that dissolved the limestone from below with a different character and speed and mechanism, carving the cave's chambers upward from the water table rather than downward from the surface. The process is called sulfuric acid speleogenesis, and its recognition, confirmed and elaborated through the 1980s and 1990s, revised the textbook understanding of cave formation in a way that is still being assimilated. It meant that the search for how a cave formed could not stop at the surface. The acid might have come from below. The cave might have grown upward. The beautiful chandelier rooms of Carlsbad and the extraordinary formations of Lechuguilla, which include some of the most unusual and spectacular speleothems known, formations found in few other caves, were products not of patient rainfall, but of a geological meeting between deep petroleum chemistry and shallow groundwater, a process that sounds almost industrial and produced something that looks transcendent, Carlsbad and Leitchegila were dissolved from below by sulfuric acid rising from oil and gas deposits. That sentence sits comfortably alongside all the carbonic acid chemistry discussed earlier, not as a contradiction, but as a demonstration that the Earth's processes are more various than any single textbook version of them. The cave as a category encompasses more than one story. Something else lurks in these sulfur-carved chambers, and in other cave systems where the chemistry departs from the simple carbonic acid model, and it is worth pausing on because it changes the picture of what a cave is. Movile Cave in Romania, near the Black Sea coast, was sealed, entirely sealed from the surface, for somewhere in the range of 5 to 6 million years, cut off from sunlight, from fresh groundwater from above, from any infusion of organic material washed in from the soil. It was discovered in 1986 when workers drilling through the limestone encountered the passage accidentally. What they found inside was alive, not in the way a show cave entrance is alive with bats and insects and the occasional confused surface creature. Alive in a self-contained way, in a system that had been running for millions of years on no energy source whatsoever from the sun. Movile Cave is fed by hydrogen sulfide rising from below, and the bacteria that have colonized the cave's warm, mineral-rich water derive their energy by oxidizing that hydrogen sulfide. They are chemosynthetic, making their living from chemistry the way surface plants make theirs from sunlight. And on the layer of bacterial mat that covers the water's surface, and in the water itself, and in the air above it, a food web has evolved. Blind spiders and pseudo-scorpions, and water lice and leech species and isopods, all of them pale, all of them adapted over evolutionary time to a world without light, many of them found nowhere else on Earth. Movile Cave is a pocket of the deep past, sealed and self-sufficient, a demonstration that life can build an entire world from chemistry alone, that sunlight is not the only engine of biological complexity. The troglobites, the true cave dwellers, those animals that have spent enough generations in the dark that they have lost the features the surface world requires, are perhaps the most quietly astonishing inhabitants of the karst. Troglobite, from the Greek for cave dweller, carries the weight of long adaptation. These are not creatures that wandered in and stayed. They are creatures that have been inside long enough that outside has become, for their lineage, inaccessible. Eyes are expensive, metabolically and developmentally, and in total darkness they are also useless, so evolution is not sentimental about them. They go. The eyes reduce, the skin loses its pigment, the sensory structures that detect water movement and vibration and chemical traces in the water amplify to compensate. The animal that remains is pale and translucent and moves as though it has all the time in the world, which in a cave, in a stable, dark, cool, food-poor environment where nothing much changes, it often does. The finest example and one of the most remarkable animals in Europe is the olm. Its scientific name is Proteus anguinus, and it is a salamander, an aquatic one, permanently larval in form, meaning it retains throughout its life the external gills it breathes with, feathered and delicate, projecting from behind its head like some impossibly elaborate headdress. It is found in the cave waters of the Dinaric karst, the limestone country of Slovenia, Croatia, Bosnia, and the surrounding region. And it is entirely blind, the eyes having reduced in the course of its evolution to vestigial traces buried beneath the skin. Its body is pale, almost translucent, a faintly pinkish white, the color of something that has not seen sunlight for a very long time. It can live for decades. Individual olms have been documented surviving for well over a century in captivity, though in the wild their lifespans are harder to establish with precision, and they can go without food for years, not days, not weeks, years. In a state of metabolic patience that has no real parallel in surface vertebrates, in Slovenian folklore, before the olm's true nature was understood, It was sometimes called the human fish, partly for its pale, fleshy appearance, partly for the strangeness of encountering it in an underground spring. And when floods pushed olm juveniles up through the groundwater and out through springs, local people sometimes found them washed out into the daylight, small and pale and entirely mysterious, and took them, entirely reasonably, for the young of dragons. Baby dragons, risen briefly to the surface from their underground world before receding back into the dark. The Olma's dragon child is a piece of folklore that carries inside it an accurate intuition. Here is something that belongs to a world beneath the world, something that has been down there long enough that it no longer resembles the creatures of the surface, something that seems to come from a different order of reality. It comes from limestone, it comes from darkness, it comes from karst, and the karst keeps its records. This is perhaps the subtlest and most surprising gift that cave formations offer, and it comes from the stalagmites, those patient, upward-growing columns of calcite building themselves from the floor, drop by drop, at 1/10 of a millimetre per year, or thereabouts, in the dark. As each layer of calcite is deposited, it incorporates into its crystal structure a chemical signature of the water that deposited it. That signature reflects conditions at the surface above the cave, how much rain fell, what temperature prevailed, what vegetation was growing, how much organic matter was decaying in the soil and releasing CO2. The chemistry of each year's or each century's drip water is locked into the corresponding layer of calcite like a note pressed between the pages of a stone book. A stalagmite is a climate diary, and it can be read. The technique for reading it is called uranium-thorium dating, UTH dating, and it depends on the fact that carbonate minerals like calcite incorporate small amounts of uranium when they form, but exclude thorium, a decay product of uranium. As the calcite ages, uranium decays to thorium at a known, steady rate. By measuring the ratio of uranium to thorium in a thin slice of the stalagmite, researchers can calculate with precision how long ago that layer was deposited. Combined with the chemical signatures in each dated layer, the stalagmite becomes a calibrated record, not just old, but precisely dated, with each layer assigned to a specific point in time. A single stalagmite, a metre tall, growing at its slow and typical rate, might record something approaching 10,000 years of climate in its layers. A larger one, from a suitable cave in a cave system with abundant calcite deposition over a long period, might preserve a record extending back hundreds of thousands of years, further back than the oldest ice cores from the polar ice sheets, further back than any other continuous archive of surface climate that is routinely available to researchers. The bands of a stalagmite read as dry periods and wet periods, as the cool, damp conditions of a glacial advance, and the warmer, differently drained conditions of an interglacial, periods when the great ice sheets were advancing over parts of the northern continents, changing precipitation patterns across the entire planet, and every raindrop that reached a cave ceiling was recording those changes in calcite, 1/10 of a millimetre at a time. The stalagmite does not know it is keeping a record, the chemistry does not know what it is doing. The calcite precipitates from the water because the water has exhaled CO2 into the cave air, and the equilibrium has shifted, and there is nowhere else for the calcium bicarbonate to go but back to calcite. It is the same reaction it has always been. But in doing so, for millions of years, in caves across the world, in Borneo and China and Kentucky and Slovenia and New Mexico and Vietnam and Romania and the Yucatan and 1,000 unnamed valleys, the stone has been writing the history of rain. Every drop that fell through a limestone hillside and reached the ceiling of a cave and let go its calcite before falling to the floor. Each one of those drops is a sentence in an archive that now extends further back into the past than almost any other record the planet keeps. This is what it means to say that the cave cathedral is not simply beautiful, it is also legible. The formations that give a cave its appearance of art or architecture, the columns, the flowstone, the draperies, the cautious and gravity-indifferent helictites, are simultaneously the columns of a library. The ornamentation is the record. The stone that looks carved is also written, and neither quality diminishes the other. Let all of this settle now, let it slow. You have followed water from the moment it fell as rain through a sky containing carbon dioxide, and took that CO2 into itself and descended through soil that offered it more, and arrived at limestone, already sour enough to begin its quiet conversation with the rock. You followed it as it found the first hairline crack and began to widen it, and widened it again, and kept widening it across spans of time that make the history of our species feel like a single afternoon. You followed it down through the vadose zone where it cut its narrow canyons, and then further into the phreatic dark where it moved under pressure in all directions and dissolved smooth tubes in the surrounding stone. You followed it as the water table fell and the tubes it had carved were left in the air, and a newer stream came down and cut a slot beneath the old rounded ceiling and made the keyhole passage that cavers recognize. You followed it as it emerged into a cave space and exhaled, and left its calcite on the ceiling as a ring the width of a single drop, and that ring extended over centuries into a soda straw, and the straw clogged and thickened into a stalactite, and below it a stalagmite rose to meet it, and they joined into a column, and the column is still growing now, still adding its fraction of a tenth of a millimetre in the dark tonight, while you are here. You have seen what the water makes when it has 1,000,000 years. The Sarawak Chamber in Borneo, 700 meters long and 400 wide, a room too large to see across, its floor a chaos of breakdown boulders in a darkness that predates any human knowledge of it. The Miao Room in China, rivaling Sarawak in cubic volume, two staggering spaces in a quiet competition conducted by surveyors with measuring equipment in places where no light has ever been permanent. Mammoth Cave in Kentucky, stretching 686 kilometres through the limestone, a length of passage that, if it could be uncoiled and laid flat, would run from London to somewhere beyond Warsaw, and it is all underground, and it was all carved by slightly sour water following cracks in ancient seafloor. The Arabica Massif in Georgia, where Veryovkina descends past 2,200 meters into the earth, a depth so great that reaching the bottom requires days and diving equipment and camps in the dark, and the cave continues past where anyone has yet gone. Son Duong in Vietnam, with its jungle growing in the dark and its clouds forming below the ceiling and its cross-sections large enough for a skyscraper to stand in, surveyed only, in the last few decades, a reminder that the Earth's interior is still being introduced to us. You have met the caves that were carved not by rain at all, but by sulfuric acid rising from below. Carlsbad Caverns and Lechuguilla in New Mexico, where hydrogen sulfide from deep oil and gas deposits met oxygenated groundwater and produced an acid strong enough to dissolve the limestone from beneath, carving chambers upward rather than downward, filling them with formations found in few other places on Earth. A reminder that the Earth makes its spaces by more roots than any single story accounts for. You have met Mobile Cave in Romania, sealed for millions of years from sunlight, running on the chemical energy of hydrogen sulfide, sustaining a food web of blind and pale creatures in water that has not known daylight since long before our species existed. You have met the olm, Proteus anguinus, pale as limestone and as patient, decades lived and eye-free, moving through the karst waters of the Dinaric caves, and the old stories that called its juveniles, washed to the surface in floods, the young of dragons, which is a misidentification so understandable, so imaginatively apt, that it deserves to be kept close. And you have learned that the stalagmites hold within their calcite layers a dated record of rainfall going back hundreds of thousands of years, that the formations which decorate the cave also archive the history of the sky above it, that the stone which looks like art is simultaneously a library, and that youth dating has given researchers the ability to read that library with enough precision to say about a layer of calcite laid down in total darkness under a limestone hill exactly when the water that deposited it fell as rain. The cave was never doing only one thing. The water was never doing only one thing. It was dissolving and recording and depositing and sheltering life and remembering climate all at once, in the dark, without anyone knowing. The chambers are quiet now. They have been quiet for longer than the word quiet usually implies. Quiet for the age of mountains, quiet for the duration of ice ages that began and ended and began again, while the stalactites grew their cautious centimetres, and the cave pearls turned slowly in their shallow basins. The Sarawak Chamber is quiet in this moment, its boulder-strewn floor undisturbed, its ceiling lost in a darkness that no torch is currently interrupting. Lechuguilla is quiet, its gypsum formations and extraordinary draperies, and the crystal complexity of its walls standing in the absolute absence of light. Movile is quiet, its warm chemosynthetic water moving gently, its pale creatures drifting through a world that has been sealed and self-contained since before our species had a name for anything. The Olm, somewhere in the karst waters of the Dinaric limestone, is drifting too, unhurried, as it has drifted for millions of years of evolutionary time, as it will drift long after the question of what to call it has ceased to matter to anything. And somewhere beneath a limestone hillside that you may never visit, in a cave that may not yet have a name, a single stalactite is growing. It is hollow at the moment, still a soda straw, the exact width of the drop that hangs from its tip in the dark, a tube of calcite perhaps a few millimetres long, perhaps a metre, perhaps 2 or 3. The drop forms and falls, and another forms in its place. The calcite ring at the tip is a fraction of a tenth of a millimetre thicker than it was last year. In 100 years it will be a centimetre longer. In 1,000 years it may be long enough that you could measure it with a ruler and feel the weight of the centuries in the measurement. In 10,000 years, if the water keeps flowing and the cave remains stable, and the limestone above it holds, it will be a recognizable stalactite, something a person shining a light upward would pause to look at. In 100,000 years it may have met the stalagmite rising below it, and the two will have joined into a column, and the column will stand in a chamber alongside other columns that completed their union before it, and newer soda straws will be beginning their own long journeys from the ceiling above them. This is happening now, tonight, in a cave somewhere, in the dark. The drop is forming. The calcite ring is thickening its fraction of a fraction. The water is moving through the phreatic dark, and the acid is working at the limestone it has not yet reached. And the chamber that does not yet exist is being prepared, grain by grain and ion by ion, by the same process that prepared all the other chambers in the same patient dark, on the same geological clock that has no hands we can see and no face we can read, but that nevertheless keeps the most faithful time of anything on earth. A raindrop fell. It borrowed an acid from dead leaves. It found a crack in an ancient ocean. And it began. Everything in the cave, the Sarawak Chamber's 700 metres, the 686 kilometres of Mammoth Cave, the 2,000 metres of descent into the Arabica Massif, the jungle and clouds of Sonjong, the gypsum beams of Nika, standing 12 meters tall in 50-degree water, the pale olm drifting through the dinaric dark, the stalagmite recording rainfall in bands of calcite nobody has yet read. Everything is that drop, followed long enough. The same weak acid, the same reversible equation, the same patience applied at the same slow rate across the same incomprehensible depth of time. The cathedral was not carved, it was dissolved, it was precipitated. It was, in the most literal sense available to chemistry, breathed. A slow geological breath in and out, the stone taken up into solution and set down again elsewhere, repeated beyond counting, across spans of time that do not fit inside a human life or a human history, but that fit perfectly inside a cave where they accumulate in layers, in formations, in the shapes of rooms so large they hold their own weather. If you are somewhere in the world tonight, in your bed, listening to this, if you are in a city above limestone, or a valley formed by a former river that dissolved its way downward through karst, or a coastal plain where the rock beneath you is chalk, which is limestone's close cousin, also the product of ancient marine life laid down in ancient seas, then somewhere below you the water is moving, not fast, not with any urgency, but moving through cracks too small to see, through passages that do not yet deserve the word passage, toward openings that do not yet deserve the word cave. The chemistry is the same chemistry it has always been. The stone is offering the same patient resistance it has always offered. And the water will win because the water has time, and time in this context means something vaster than we can properly imagine, but can perhaps, on the edge of sleep, begin to feel. Let the stone work in the dark. Let the drop form at the tip of the straw. Let the olm drift. If you feel moved to share where in the world you are listening from tonight, I would genuinely like to know. The comments are there, and I do read them. And there is something particular about knowing that these slow stories reach people in different countries, different time zones, different rooms above different geology, some of them perhaps directly above limestone, some of them far from any karst. Tell me where you are. Tell me what is beneath you if you know. And if you are new here, there are more stories of this same slow and patient kind, waiting for whenever you want them. The history of the earth is long, and there is no shortage of things to descend into together. You have done enough for one night. Let whatever you were carrying before you came here rest now. The carbonic acid is working in the dark, as it has always worked. The chambers are quiet. The stalactites are adding their fractions of a millimetre. The water table is where it is, and the phreatic tubes are full, and the vadose canyons are carrying their slow streams downward by gravity, and none of it is in any hurry, and none of it requires your attention, and all of it will still be there. History will still be here in the morning. For now, rest.